Why was the universe born with a reservoir? You can think of it as a reservoir of order which can unravel over billions of years and allow complex structures to exist. In January of 2025, Google's Quantum AI lab did something no one expected. They took raw, unprocessed, deep field data from the James Webb Space Telescope and ran it through one of the world's most powerful quantum processors. The result? Anomalies, light distortions, and energy patterns that shouldn't exist in our universe. Within the first few seconds of processing, quantum correlations emerged that defied every model of gravity, dark matter, and cosmic dust. Yes, you heard that right. The quantum computer saw clues of a reality that might be overlapping with our own. So, is this a glitch in the code? A software artifact? Or have we just glimpsed the edge of a parallel universe? Stick around, because by the end of this report, you'll see the data, the theories, and the jaw-dropping implications for everything we thought we knew about reality. Quantum AI meets James Webb. In early 2025, Google's Quantum AI team partnered with astrophysicists at Caltech to tackle a problem classical supercomputers couldn't solve: modeling the full quantum state of cosmic light. They pointed the quantum processor at raw photon counts, spectral curves, and gravitational lensing maps from Webb's deepest field exposures. Data that had sat untouched, waiting for the right tool. Within hours, the quantum system produced a set of anomalous signatures. First, there were energy distortions. Bands of infrared light shifted in ways no known process could explain. Next, the AI detected non-local correlations between photons arriving from distant galaxy clusters, implying a hidden variable influencing multiple sightlines simultaneously. The team ran the analysis dozens of times, each with fresh random seeds. Every run showed the same patterns: wedges of light appearing and vanishing in sync, as if another cosmos were briefly bleeding into ours. But the biggest shocker came when they mapped these anomalies onto spatial coordinates. They formed geometric arcs, not random speckles, but structured formations that repeated across separate fields of view. This wasn't noise, it was a signal, a footprint of something beyond our space-time. If this kind of reality-shaking discovery gets your mind racing, keep reading. To grasp why this matters, let's rewind. Classical supercomputers can simulate cosmic structures at scale, but only by approximating quantum effects. They collapse probabilities into averages, smoothing out the very phenomena that might reveal new physics. Quantum computers, in contrast, process information in qubits, which can exist in superpositions and capture entanglement natively. That makes them uniquely powerful for modeling multi-particle quantum systems, like vast clouds of interstellar photons influenced by gravity's quantum corrections. When the James Webb Telescope launched in 2021, it promised to show us the earliest galaxies. It delivered breathtaking images of star nurseries and ancient galactic collisions. Yet, those images were processed, cleaned, and interpreted using algorithms built for classical hardware. Google's team asked, what if we feed the rawest form of Webb data? No filters, no averaging, straight into a quantum processor? What hidden structures might lurk beneath our assumptions? The answer was astonishing. Light patterns that suggest interference from a dimension we can't directly perceive. And these patterns aren't subtle. They span tens of arc minutes and intersect with known dark matter filaments. By 6 a.m., the scientific community was buzzing. Are we on the verge of detecting quantum leakage from a parallel domain? Enter brain cosmology. In string theory, extensions like M theory, our universe is just one brain floating in a higher dimensional bulk. Other brains could exist right next to ours, separated by imperceptible distances in extra dimensions. The idea of quantum leakage proposes that, under certain conditions, especially where gravitational fields are strong or quantum fluctuations intense, information can tunnel between neighboring brains. In our case, the quantum AI saw phase correlations between photon states that match predictions of brain interference. These anomalies persisted across multiple wavelengths, from near-infrared to mid-infrared, ruling out simple contamination by cosmic dust or instrumental noise. Instead, they traced coherent patterns that align with mathematical models of overlapping universes. Bold question. What if the James Webb Telescope has been inadvertently peeking through the cracks in our reality, glimpsing photons that have drifted across from another cosmos? When you watch these arcs of distorted light, you're not just seeing the far side of a galaxy. You might be looking at echoes from a parallel world. A mirror geometry. Just when it seemed we'd hit the limit of speculation, a second anomaly appeared, a gravitational mirror. By overlaying the anomalous photon maps onto known dark matter distributions, researchers noticed a symmetry that shouldn't exist. Galaxy clusters on one side of the field were bent by gravity, as expected, but clusters on the opposite side bent in the exact opposite direction, as if there were a reflective boundary at the center. This gravitational mirror effect turned out to be consistent across 3 separate sky patches. It looked as though massive structures in a parallel brain were exerting a gravitational pull on our photons, then reflecting them back. One researcher described it as like standing between 2 halls of mirrors, but the other image is a universe we can't step into. It was a feedback loop, a cosmic hall of mirrors that challenged our notion of isolated space-time. At 11 a.m., the team realized they weren't just mapping anomalies. They were charting the contours of another cosmos. Pause and consider. If universes can brush up against one another, what does that mean for our understanding of reality? Are the laws of physics different next door? Do stars burn hotter? Does time flow the same way? Take a moment to let that sink in. Now, let's take a step beyond the raw data, beyond patterns and light distortions, and walk into the territory where physics meets philosophy. It starts with John Wheeler, one of the great minds behind modern quantum theory. Wheeler proposed something bold and unsettling, that the universe is not a static, objective thing waiting to be observed. Instead, it participates in its own creation. He called it the participatory universe. According to Wheeler, the very act of observation, of measurement, helps bring the universe into being. Reality isn't entirely there until it's interacted with, until it's seen, until something, a mind, a machine, an observer, asks the universe a question. This idea, once a philosophical musing, now gains startling new relevance in the age of quantum AI. Because what happens when that observer isn't human at all? What if it's a quantum computer, one powerful enough to model entangled systems across billions of qubits? When Google's quantum processor was trained on unprocessed James Webb photon data, it wasn't just performing calculations. In quantum terms, it was interacting with raw, probabilistic information. It was measuring wave functions that had never collapsed, photons that, in a sense, had never been fully observed. And when it did, something strange happened. Instead of a clean image or straightforward noise, the processor began surfacing data structures that hinted at something more: dimensional overlays, non-local entanglements, mirror symmetries across deep field frames. Could the quantum computer have done something no telescope could? Could it have, by its very act of processing, forced those photons to collapse into states that revealed hidden dimensions? Let's go deeper. Enter the many worlds interpretation of quantum mechanics. This is one of the most radical, yet increasingly discussed, views in physics. According to many worlds, every quantum event, every particle spin, every photon path, every decision at the quantum level splits the universe. Branches of reality multiply outward endlessly, spawning countless parallel versions of events that almost happen. In one, the particle spins left. In another, it spins right. In both, reality continues, just slightly differently. Normally, these branches don't interact. Each world goes on, unaware of its counterparts. But what if that boundary isn't absolute? What if a sufficiently powerful quantum system, like Google's quantum AI, could entangle not just particles, but entire probabilistic frameworks? What if it became a kind of interdimensional observer, aligning probabilities across branches and giving us flickers of what could have been? What the AI started detecting wasn't just unexpected structure in the photon data. It was something else, something that felt off-angle, slightly out of sync with our known universe. A mirror reality glimpsed not through a telescope, but through quantum entanglement itself. Think of it this way. If every observation locks in one version of the universe, what happens when millions of quantum measurements are made simultaneously across a web of entangled qubits, interpreting raw cosmic data? Does it create resonance? Does it momentarily align our branch of the universe with others? Could we be seeing ghost signals from realities that almost but didn't come to pass? One physicist involved in the project put it hauntingly: we're not just looking at the universe might be looking back through all its versions. Suddenly, the boundaries between science, philosophy, and metaphysics begin to blur. Suddenly, Wheeler's ideas don't sound so abstract. Suddenly, quantum computation becomes more than a tool. It becomes an ontological lever, a way of peeling back the layers of reality, one calculation at a time. And maybe that's why this moment matters so much, because we've spent centuries trying to observe the cosmos as outsiders, gathering light, analyzing patterns, interpreting signals from a supposedly indifferent universe. But what if we're not outsiders at all? What if every observation, every algorithm, every quantum decision feeds back into the very structure of reality? What if our curiosity shapes the world we live in, not metaphorically, but literally? The data suggests something is happening, something new. A threshold is being crossed. And the more we probe, the more the boundary between what is and what might be begins to melt away. So, we ask again, are we seeing ghost signals from the choices reality almost made? The question sounds poetic, but in this case, it's grounded in actual quantum data. Data that refuses to settle into easy answers. Data that whispers of something just behind the curtain of perception. This isn't just a scientific moment. It's an existential one, because the implications are staggering. If reality responds to observation, if quantum computation can align dimensions, if alternate timelines can cast shadows into ours, then maybe, just maybe, the cosmos is alive with potential, and we are co-authors of the universe, writing its story one measurement at a time. And maybe the act of looking is also the act of creating. Code hidden in the light. Just when you thought this story had already tipped into the surreal, it went one step further. In a quiet, late-night test session, a sub-team of researchers decided to analyze what everyone else had ignored: the spectral noise, that faint, chaotic hum riding alongside the deep field images, usually filtered out as background error. But this time, they didn't filter it. They fed it into a prime number decomposition model, usually reserved for cryptographic analysis, just for fun, just to see. And what they found shook the room. Instead of a random, noisy distribution, as you'd expect in cosmic background signals, the amplitudes of fluctuation snapped into alignment with something eerily specific. The first 101 prime numbers, not in one data set, not in one region of the sky, but across multiple wavelengths, angular scales, and observation epochs. It was as if the noise had been sculpted, like something or someone had intentionally encoded the primes into the deepest layers of light. The odds of this happening naturally? Vanishingly small. Statistically, it's the equivalent of flipping a coin 1,000 times and landing heads every single time. So, two possibilities rose from the data, both almost equally unthinkable. First, natural artifact. There might be some unknown astrophysical mechanism, perhaps gravitational lensing combined with quantum interference, that, under rare conditions, mimics prime-based patterns in light. It would have to be a phenomenon we've never seen, never modeled, and have absolutely no current explanation for. A long shot, but science has been surprised before. Second, intentional signal. This wasn't an accident. Instead, it may be a deliberate mathematical signature encoded into the structure of the universe itself, either from an intelligent species in a parallel brain or from something even older, something primordial, a cosmic intelligence that predates stars, galaxies, and time as we understand it. Because primes are universal, they don't depend on biology, chemistry, or even physics. They're baked into the structure of logic itself. If any intelligence wanted to communicate across dimensions, civilizations, or even universes, prime numbers would be the purest medium. Just think about that. A message written in light, composed in the alphabet of mathematics, transmitted not through space, but through reality itself. Naturally, the team was skeptical. They double-checked everything. Instrument calibration errors? Ruled out. Terrestrial interference? Cross-referenced and eliminated. Solar reflection anomalies accounted for. The pattern still held. Then they went one step further. They compared the Webb data with raw data from ESA's Euclid mission, which observes different sky regions using different instruments from a different Lagrange point. Same pattern, same primes, no overlap in observation equipment. The data couldn't be explained away. And at exactly 18 minutes and 30 seconds into the final review session, one of the lead investigators, a quantum information specialist not prone to metaphors, leaned back in her chair, looked at the team, and said softly, "This feels like a handshake. Not a signal, not a message in the traditional sense, but a handshake, a mutual recognition, a meeting point between our world and something else. A handshake across dimensions, encoded not in sound, not in symbols, but in pure number theory, projected through the fabric of space-time. The implications? If this is real, if this prime pattern is intentional, it would be the first mathematically structured non-human signal ever detected in the cosmos, and not from another planet, but from another reality. A ripple in the quantum veil, a whisper through the gravitational mirror, a nod from something watching. Maybe not life as we understand it, maybe not even consciousness in a biological sense, but something capable of recognizing patterns and sending them back. And what better way to say, "We see you," than with primes, the ancient, indivisible building blocks of all mathematics? If true, this would mark the first contact event, not with aliens, but with the architecture of the multiverse itself. It redefines what we mean by signal. It redefines what we mean by communication. And it suggests that maybe, just maybe, we're not the only ones doing the observing, because for the first time, light may have answered back. What it means for reality. Let's zoom out, because what we've just uncovered might be the beginning of a new worldview. We started with raw, untouched data from the James Webb Space Telescope, not the stunning images the world saw on launch day, but the raw photon data, the cosmic noise most systems discard. We fed that into a quantum processor capable of modeling entanglement across billions of variables. And what emerged wasn't chaos, it was structure. We found light distortions, arcs, and ripples bending in directions classical physics couldn't explain. We saw non-local correlations between galaxies millions of light years apart, as if a hidden hand was shaping their positions. We discovered a gravitational mirror, a reflection of mass from a place that shouldn't exist, a cosmic echo bouncing back from what might be a parallel brain. But the weirdness didn't stop there. The quantum system picked up observer-linked phenomena, outcomes that seemed to change depending on how the data was measured or viewed. It was as if reality itself was participating in the computation, blurring the line between simulation and interaction. A direct nod to John Wheeler's participatory universe. And then we uncovered something that stopped even the skeptics, a prime number pattern embedded in the light, coded into the spectral noise across different sky regions. Not a random fluke, not instrumentation error, but a structured mathematical sequence emerging from the deepest reaches of space. Let that sink in. It could all be an astonishing string of coincidences. That's the conservative take, a handful of anomalies misread through the lens of high technology and cosmic curiosity. But maybe, just maybe, it's not coincidence at all. Maybe this is the first tangible evidence that our universe is not alone, that what we call reality is only one layer in a stack of universes, gently brushing against each other in ways we're only beginning to detect. A grand multiversal weave, stitched together by logic, probability, and quantum computation. Because if photons can tunnel across brains, if observation can shape the behavior of matter across dimensions, if numbers, the purest language we know, can pass between realities like messages in a bottle, then we're not just observing the universe anymore. We're communing with it. This isn't just science. It's something deeper, a confluence of astronomy, quantum mechanics, information theory, and metaphysics, an inflection point where hard data begins to whisper philosophical truths. Maybe we haven't just built better instruments. Maybe we've cracked open a window into something vast, recursive, and alive with meaning. And now, standing at that threshold, one truth rises above the rest. Our universe is not sealed. It leaks. It mirrors. It responds. And we, armed with quantum AI and a telescope gazing deeper than ever before, may have just heard the first reply. Not in language, not in sound, but in the only voice the cosmos has ever used. Light. And light, it seems, is trying to tell us something. We just have to keep listening. If this revelation has you questioning everything you know, consider following along for more explorations of cosmic mysteries.